In this video, we're going to be discussing the problem of the inverted pendulum on a cart and taking it through to be able to do a state space analysis so that we can um, apply just a single force on the block or on the cart to keep the pendulum up in this unstable or uh, yeah, in this unstable position. So we have a cart here that's sliding with friction or without friction on the ground, and attached to the cart is a pendulum. So the cart has a mass ma, the pendulum has a mass mb. We're also going to introduce some inertia of the pendulum equal to 1/3 mb L squared, where L is the length of the pendulum itself. And so we have a coupled set of nonlinear differential equations here. The first row, ma plus mb x double dot plus mb L cosine theta times theta double dot plus mb L sine theta times theta dot squared is equal to Fc, which is again that force applied to the cart or the block. And then the second equation, MBL cosine theta x double dot plus IZZ plus MBL squared theta double dot minus MBGL sine theta. And all of that is equal to 0. So we're going to be doing a couple things, or a few things in this video, in this example. The first thing that we're going to do is we're going to linearize the equation. So this is a nonlinear set of differential equations. We see sine theta, cosine theta, theta dot squared. All of these are nonlinear terms that make analysis more difficult. So we're going to linearize to make our analysis simpler so that we can use some of the tools that we've been learning about. And once we've linearized it, we will be left with a linear set of coupled differential equations. So we'll um, express the set of equations in matrix form. And once we do that, expressing it in matrix form will be a step towards uh, expressing the same set of differential equations in state space, and that'll allow us to develop a controller for this system so that we can choose a value of Fc that gets our system to be, so we can choose a value of Fc that allows the pendulum to stay upright. Okay, so I've turned off this suggest math results feature, so hopefully those boxes will stop showing up. But let's proceed with linearizing the equation. So the first thing we need to do when we linearize is we need to determine a nominal point around which we are going to linearize. Usually you would do that by setting your derivatives x double dot equal to 0, theta double dot equal to 0, and we'll go ahead and say that theta dot is equal to 0, x dot is equal to 0, and we'll just choose an arbitrary position. So we'll say that x is equal to some x nominal, and theta is equal to some theta nominal. And so the first thing that we'll do is we can plug these nominal values into our original differential equation so that we can determine a nominal force and see what else the equations will tell us about what's going to happen at these nominal values. So from our first equation, we'll have ma plus mb x double dot, which will be 0, plus mb L cosine of theta nominal times theta double dot, which is 0, minus mb L sine of theta nominal times 0 squared is equal to FC nominal. And then the second equation, MBL cosine theta nominal times 0, x double dot nominal, plus IZZ plus MBL squared times theta double dot is equal, nominal is equal to 0, minus MGL sine of theta nominal equal to 0. So we've got a few zeros multiplied in here, so we can come up with a couple things. So first, we know that FC nominal, our nominal control force to maintain a nominal point with zero acceleration, zero velocity, is equal to 0. That comes from the first equation. And we also know that MB times GL sine of theta nominal is equal to 0. So we would need to find a nominal position where sine of theta nominal is equal to 0, because MB and G and L are not going to be equal to 0. So um, so we'll take take that information, FC nominal equals 0, and MBG L sine theta nominal equal to 0, and we'll save that information for later. But what we'll do now is we'll define perturbations from the nominal point. So we'll say x tilde is equal to x minus x nominal, theta tilde equal to theta minus theta nominal. That means because x nominal dot is 0, x tilde dot is equal to x dot, and x tilde double dot is equal to x double dot, and same for thetas. Theta tilde dot is equal to theta dot, theta tilde double dot is equal to theta double dot. And FC will define a perturbation from our nominal force as well, is equal to FC minus FC nominal, the nominal force, and that one we already determined is equal to 0. And so we can use these relationships right here and plug them back into our original equations up here to express these differential equations in terms of a different variable, theta tilde. And we do this because when we're trying to linearize, we want to be able to work under the assumption that the dependent variables are remaining small, and so we define these errors as a new dependent variable. So I'll go ahead and we'll start plugging things in. MA plus MB times x double dot is equal to x tilde double dot plus MB L cosine theta is equal to theta tilde plus theta nominal, and that's multiplied by theta double dot, so theta tilde double dot, minus MB L sine theta is equal to theta tilde plus theta nominal times theta tilde dot squared equals FC tilde. FC is equal to FC tilde plus FC nominal, and FC nominal is equal to 0. The second equation, MBL cosine theta is equal to theta tilde plus theta nominal, x tilde double dot, plus IZZ plus MBL squared theta tilde double dot minus MBGL sine theta tilde plus theta nominal. Theta tilde plus theta nominal is equal to theta, and that equals 0. And so what we'll do is a little bit of trigonometric identities to make sure to get rid of these cosine of a plus b and sine of a plus b type terms. So we'll say sine of theta tilde plus theta nominal is equal to sine theta tilde plus or times the cosine of theta nominal plus sine theta nominal cosine theta tilde. And so in this case, sine of theta nominal, we already determined from this equation right here, has to equal 0. So that second term goes away. And so we're left with, wherever we see a sine of theta tilde plus theta nominal, we can plug in the sine of theta tilde times the cosine of theta nominal. We'll do the same thing using a trig identities for the cosine of theta tilde plus theta nominal. So that's going to equal cosine of theta tilde times the cosine of theta nominal minus the sine of theta tilde sine of theta nominal. And same thing, we see a sine of theta nominal. That term goes to 0. Cosine of theta nominal is going to be a constant, so that can be treated as just a coefficient in front of sine of theta tilde in that first equation for the sine, and the cosine of theta tilde in that second equation. And so we can plug these back into these two equations right here. And so what we have is MA plus MB x tilde double dot plus MBL cosine theta tilde cosine theta nominal minus MBL sine theta tilde cosine theta nominal theta tilde dot squared is equal to F C tilde. And the second equation, MBL cosine theta tilde cosine theta nominal multiplied by x tilde double dot plus I ZZ plus MBL squared theta tilde double dot minus MBGL sine theta tilde cosine theta nominal is equal to 0. So we have two equations where everything is in terms of something that we've used small value approximations in the past to linearize it. So we can take these two equations and we can linearize them. So this first term, MA plus MB x tilde double dot, is linear already. The cosine in this second term right here, the cosine of theta tilde will linearize to 1 if theta tilde is small, so it'll be MBL cosine theta nominal. Cosine of theta nominal is a constant. I'm missing a theta tilde double dot right there, but so that gets multiplied by theta tilde double dot, and then minus the MBL sine theta tilde. That sine theta, well, actually, that sine theta tilde would linearize to just theta tilde, but it's also multiplied by this theta tilde dot squared. So that whole term goes to 0 because the theta tilde dot squared linearizes to 0 as an approximation. And so that's all equal to FC tilde. And then the second equation, the cosine theta tilde in the first term here linearizes to 1, so it's MBL cosine theta nominal times x tilde double dot plus IZZ plus MBL squared theta tilde. That's a linear term, so we'll leave it as it is. And then the minus mbgl sine theta tilde. The sine theta tilde will linearize to just theta tilde. So we're looking at mb times g times l times that cosine of theta nominal is a constant, theta tilde equals 0. So we have a set of linear second order differential equations here that are the linear approximation for the inverted pendulum on a cart. And so that was the first thing that we said we were going to do in this video was linearize. The next thing that we're going to do is we're going to express these differential equations in matrix form. And we'll express it as second order m, capital matrix M, mx double dot plus b x dot plus k x is equal to some vector g times fc tilde, where the vector x is equal to x tilde theta tilde. And that means that the vector x dot is equal to x tilde dot and theta tilde dot. And same thing for x double dot. So to build these matrices, what I need to do is, for the mass matrix M, pull off all of the coefficients of in each equation that have that are on the x tilde double dot term and the theta tilde double dot term. So what I'll have is, in the first equation, I have MA plus MB is the coefficient of x tilde double dot, and MBL cosine theta nominal is the coefficient in front of theta tilde double dot. On the second equation, or second row of this mass matrix, MBL cosine theta nominal is the coefficient on the x tilde double dot, and I ZZ plus MBL squared is the coefficient in front of theta tilde double dot. So I'll have an x tilde double dot here, a theta tilde double dot there. And then there's actually no theta dot terms in here, so there's no B matrix, so we'll skip straight to a K matrix. So in the first equation, we don't actually have anything that's on x tilde or theta tilde. Second equation has nothing on x tilde and just a minus m b g l cosine of theta nominal. And that equals the matrix 1, 0 times fc tilde, where fc tilde is our input force. And fc tilde only shows up in the first equation and not the second equation. So now that we have a matrix form of these equations, and this is again a matrix form of our system of equations that represents the inverted pendulum on a cart system, we're going to try and see if we can make it a little simpler for ourselves by adding taking another step into state space form. You'll notice that the equation that we have written here is a second order coupled differential equation. And what we can do is we can re-express this as a system, as a larger system of first order equations. So we'll express it in state space, first order with some y dot is equal to a matrix A times y, and then because it's inhomogeneous, we'll add some vector B times fc, or y is equal to x tilde theta tilde x tilde dot theta tilde dot. That means that y dot is equal to x tilde dot theta tilde dot, x tilde double dot, and theta tilde double dot. And we can relate this to our second order, to our matrix space, or our matrix form, by saying that we can also say y is equal to our vector x and the vector x dot. And this is in a block notation. So we can, from our earlier matrix form, we can isolate mx double dot is equal to minus kx plus g times fc tilde. And we can start to construct this y dot equals ay plus bfc matrix. So y dot is equal to x dot capital X double dot. And we're going to have a matrix A multiplied by the vector y, x dot, that vector is the 4x1 vector y, plus something else times fc. And so x double dot we already determined is equal to, mx double dot is equal to minus kx plus gfc. And so if we wanted to isolate just x double dot, we'd have a minus m inverse x time, or minus m inverse k times x, and 0, no x dot term. And then x dot is equal to itself, 0 times x plus the identity matrix times x dot. X dot doesn't have any fc terms, but x double dot will have this term right here multiplied by m inverse times g fc. So this matrix right here is A, this matrix right here is B, and so we filled out the y dot equal to ay plus b fc. And so we have these expressed in block form, or block matrix form, and we've got this m inverse, so we need to be able to calculate the inverse. M inverse is equal to 1 over the determinant of m times the adjoint of m. The determinant of m, we already figured out the matrix, the mass matrix is ma plus mb times I zz plus mbl squared minus mbl squared. I'll go ahead and simplify and rewrite that. The determinant of m is equal to izz ma plus mb plus ma mb l squared. And then we can rewrite this. The inverse of the matrix M is equal to 1 over that determinant I zz ma plus mb plus ma mb l squared. That is all underneath the fraction. And then the adjoint will swap the diagonals, izz plus mbl squared. And at this point, we have our mass matrix, which is up here. Cosine, we've got MBL cosine theta nominal in the off-diagonal terms, and we'll choose the value of theta nominal that we want. We'll say it's equal to 0, keeping this pendulum upright. So cosine theta nominal is 1, and minus MBL, because we have a minus our off-diagonals there, and then MA plus MB. So this is our value of the inverse of M. And now we can write the full 4x4 of the matrix A. So we had zeros in the top left. So 0, 0, 0, 0. We had an identity in the top right. And then um, in the bottom left, we had minus M inverse K. So if we were to multiply that out, we have zeros in this column, minus GL squared MB squared over the denominator that shows up in the matrix in the mass inverse, IZZ MA plus MB plus MA MB L squared. All that's under the denominator. And the rest of that minus M inverse K multiplication, we have a GLMB times quantity MA plus MB over IZZ times MA plus MB plus MA MBL. Go ahead and move our identity matrix over a little bit to make room for what's below it. And then we have a 0 block matrix in bottom left or the bottom right. So that's the matrix A. And the matrix B was equal to zeros and then M inverse G. And that turns out to IZZ plus MBL squared over that same denominator, IZZ MA plus MB plus MA MB L squared. And M inverse G, the second element, is L minus LMB over IZZ MA plus MB plus MA MB L squared. So again, in state space, we have y dot is equal to AY plus B FC. I'll spare you writing out the matrix A and the matrix B again, but they're right here with y equal to that vector and y dot equal to the derivative. And so now that we're in state space form, we can choose some value, we can choose a value of FC of that control input to control this thing or this inverted pendulum to stay inverted even if we have disturbances. And what we'll do to do that is we'll say FC is equal to some vector KC times Y, where KC is equal to a vector of control gains, K1, K2, K3, K4, and Y again is equal to X tilde, theta tilde, X tilde dot, theta tilde dot. And if we multiply these together, this turns out to be a 1 by 1. It equals K1 X tilde plus K2 theta tilde plus K3 X tilde dot plus K4 theta tilde dot. And when we multiply these, multiply that into FC, we can see that B FC, that BFC term, is going to equal the b vector, which we wrote down what it was up here, times um, FC is equal to KC times Y. If we can plug that back into Y dot is equal to AY plus BFC KCY, then this is no longer an inhomogeneous differential equation. It's a homogeneous one. We can rewrite this as Y dot is equal to A plus BKC times Y. And we can call this matrix A bar, and A bar is going to be what's called the controlled state matrix, or uh, state matrix of the system. And what we can do is we can look at and explore how those different values of K1, K2, K3, and K4 affect the stability of the system. And that'll be in the homework assignment, and that'll be something that you can play around with in MATLAB using the eig command to see how those different values of K1 through K4 change what the eigenvalues are, and uh, the eigenvalues are the poles of the system, or and will tell you whether or not you found control input or control gains that stabilize the system.